Okay, guys, let's go. We are in the middle of this chapter about magnetization and permeability. In this session, we try to figure out the new relationship between MF5 and the density, the magnetic flux density B. Okay, we don't have much time, so I will come directly to that new relationship. Here it is. So before this moment, we knew that B is equal to mu0 times H, in which mu0 is the permeability of the free space. But now, if we work in something different than the free space, I mean vacuum, then the new relationship is B is equal to mu H, in which mu here is a permeability, and it is related to mu0 by this relationship. In this one, mu r is a relative permeability. Okay, so from now on, instead of writing B is equal to mu0 H, we can write something like this. Okay, then we come to the next one. This is about the boundary conditions for a magnetic environment. This is a third kind of boundary conditions, like two previous ones. This one is that if we are given the field in one environment, then using the boundary conditions, we can find field in the second environment. Because we discussed about boundary conditions so many times before, so in this session, I will come directly once again to the final result. Here we are. We have a set of two boundary conditions, the normal one and the tangential one. Okay. I read once again that if basing on these boundary conditions, if we are given H1, for example, we can compute H2 and vice versa. Okay. To understand better this very important thing, we should do two exercises. This is the first one. When Z is positive, we have the reason number 1 with the corresponding permeability of 4. Okay. And when Z is negative, we have the second, we have the second reason. So by reading this, you can imagine, you can figure out that the boundary separating the two regions here is the XY plane. Okay. So on the boundary, meaning that on the XY plane, when Z is 0, we have a surface current density. And this current is flowing alongside the positive direction of the x-axis. Now, in the reason number 1, we are given a field B1. We have to find B2. Okay. So, in order to apply boundary conditions, we have to know the normal component and the tangential component. To find the normal component, please keep in mind that the boundary here is the xy plane. So the normal vector of the boundary is the z-axis. Or we can say that it is AZ. Okay. So if you want to find the normal component, you have to project the given field here on the z-axis. And then we have this. Are you okay? One more thing you have to pay attention. It is a unit of B. Normally, the unit of B is a millitesla, not Tesla. Okay. Be careful about this. So we found Bn1. Do you know why this one is minus AZ? Because by definition, AN12 is from the region number 1 to the region number 2. Okay? From 1 to 2. And in this exercise, number 1 is positive Z, number 2 is negative Z. So the direction of AN12 here is from positive to negative. And that direction is opposite to the positive direction of AZ, of Z axis. So this one is minus AZ. Are you clear? Okay, so we found BN1, and according to this, we can find BN2. Okay, according to the normal boundary condition, we can figure out immediately BN2. Here we are. Okay, that was a story about the normal components. Now we have to find, of course, the tangential components. B1 is a summation of normal and tangential components. So from this, we can find very easily the second component or the first field. Now, if we want to apply the tangential components, you see, we have to transform this one into H. Then, of course, this one corresponds to this equation. So we have to take into account the permeability of the two environments. Okay. All right. So from B, we can find H by applying the formula that I showed you in the very beginning of this morning. Are you okay? Do you have any question for this? Okay, keep going. So we found the tangential component of MF5 of the first environment. So we can apply the second boundary condition. This one, okay. So we apply that tangential boundary condition. In this equation, in this expression, we are given K. We just found HT1. So finding HT2 from this one is not very hard, I think. Okay. You are. From this, we can figure out HT2. Please notice that AN12 is a normal unit vector. Its direction is from the first region to the second region. According to the orthogonal method, we can compute the cross product by applying this determinant expansion. But I recommend you that you should compute this one directly, like AZ cross AX is AY, okay? And simplifying this expression here, we can finally choose the tangential component of the second environment. So this one is HT2, and we have to find B2. So once again, we have to transform this one from H to B by using, of course, the permeability of the second environment, which is mu2. Hiểu á. And finally, B2 will be the summation of the two just found components. Okay, we got Bn2, we got Bt2, and here you are. Are you okay? Any question? This knowledge is very important, so we should practice a little on this. In order to do that, I want you to do the first mid-class exercise this morning. Okay, I changed the conditions one a little. When y is negative, we have the reason number 1. When y is positive, we have the reason number 2. And then please redo this exercise. Okay, I change the given condition. This one is z, then I change to y. This one is z, I change to y. Okay. All right, I give you 8 minutes. You can ask me anytime. Okay, time out. Keep going. In this exercise, we have 2 reasons, actually 3, because this one and this one are the same. So, in the first reason, you can see that the permeability here is very, very high. It is 1,000 times greater than that of the vacuum of the free space. Okay, and in the reason number 1 here, we are given a uniform field. The direction and the magnitude of this field is constant. And please notice that the field in this region is very strong. It is about 1.2 Tesla. Now we have to find the field in the air, in the free space. Okay. So of course we once again have to find the normal components and the tangential one. This is the first boundary condition. And to find the normal component, we have to project the given field onto the normal unit vector, which is this. Okay. And to project this one onto this, you can, for example, multiply this vector to cosine of 30 degrees, like this. And then to find the remaining component, I mean the tangential one, we firstly use this component, this condition. And of course, we have to rely on the given permeabilities of 2 reasons. And to find the tangential component, which is this one, then you have to project this vector onto this direction. And you can do that by, for example, multiplying this one to sine of 30 degrees, like this. And then the question here is to find the magnitude of B in the gap. So here you are. So I want you to focus on these 2 results. The tangential component is 0.06 millitesla, and the normal component is 1 Tesla. It is approximately equal to the total field in the air. And by looking at this and this one, you can see that the tangential component is very, very small compared to the normal component. And that leads us to the conclusion saying that in the air, the magnetic field is nearly perpendicular to the surface of the magnetic material. Okay. In the air, the magnetic field is nearly normal to the surface of a magnetic material. I think you can take that comment down to your notebook, because that comment is very important. Are you okay? Okay, keep going. So in this session, we're going to talk a little about the way to analyze a magnetic circuit. And that technique is based mainly on the similarity between electric circuit, a DC electric circuit, and a magnetic circuit. In this page, you can see that there is similarity between the electric field and the magnetic field, like this. Okay, so we can use the technique that how can I say that we took from the course, say from linear circuit, to analyze the magnetic circuit. Okay. This one is an example of a magnetic circuit. Normally, it consists of a coil and a core. Okay, and when we feed a DC current to the coil here, we know that that current will produce a magnetic field, and the coil here will conduct that magnetic field to somewhere else that we want it. Okay, the core here is normally made of iron, and the core here has an effectiveness like a wire in a circuit, in an electric circuit. It conducts the magnetic fields, the magnetic flux from one position to another position. If we don't use a core, then you can see that the magnetic flux is scattered everywhere in free space. By using an iron core like this, you can see that the magnetic flux is how can I say, is concentrated at a position that we want it to be. Okay, so analyzing a magnetic circuit is to find the currents, the fields, for example. So in the process of analyzing a magnetic circuit, unlike analyzing an electric circuit, we use only three formula and three only. The first one is scalar potential, the scalar magnetic potential, VMAB. Okay, long time ago we knew that Vm is the line integral of h dot dn from A to B. But inside the core here, we can suppose that the magnetic field is nearly uniform, meaning that h here is a constant. So VMAB is approximately equal to HL. A second important equation, the second equation, okay, they are all important, is magnetic flux. By definition, it is a B dot ds integration, the surface integration of B dot ds. But like I told you, because H here is nearly uniform, so B is also nearly uniform, and then phi will be B times S, in which S here is a cross-sectional area of the core. And the last one is Ampere's law. If we take the integration of H dot dn alongside the this one, the average line of the coil here, the result will be the total current flowing through the closed line here, and that is the number of turns n multiplied to the current I. Any question? Okay, to illustrate the technique of analyzing a magnetic circuit, we do, of course, several examples. This is the first one. We have a very simple magnetic circuit. It consists of a coil and a core. Okay. The average length, which is this line, is 0.6 meter, and the cross-sectional area of this one, S, is 16 centimeters squared. The number of turns of this coil is 500. We had to find the current fed to the coil to produce a magnetic flux of 1.6 milliweber in the core. For this magnetic material, we are given this curve. This one is the relationship between MFI and magnetic flux of the core. All right. Firstly, because we are given phi, so we can start from this equation. Phi is Bs. In this equation, we of course are given phi, and we are also given S. So from this, you can find very easily the density, 1 Tesla. Please notice that you have to transform this one into a standard unit, which is a meter squared. Okay. So, any questions so far here? All right. So from B, we can find H. Normally, we can use the relationship saying that B is a mu H, but that equation, that relationship can be applied only to linear material. For our material here, the relationship between B and H is not a straight line, it is a curve. So if we are given B, we can find H by using this curve like this. 1 Tesla is here. So from this, you can take a look to find the corresponding H, and it is 200 ampere per meter. Are you right? So the given curve here is to find B if we have H, and to find H, of course, if we are given B. Any question?
Excuse me. Can you explain why H equal 200?
Okay, look at this. When we found sorry, because we found that B is 1 Tesla. So from 1 Tesla here, we go to the left horizontally. This line crosses the given curve at this point, and from this point we go down vertically, and from this axis we can read that the corresponding value here is 200.
Okay.
Please notice that if 180 or 210 is okay for me. All right.
Sorry.
Yeah. Yes. Go ahead.
What did you say? I can't hear clearly due to connected internet.
Okay, I told you that my eyes tell me that this value is 200.
Yes.
If your eyes are keener, you can say according to my eyes, this value is 200. According to your eyes, it can be 180 or 210. It is okay for the solution. Okay, so I'm talking about the accuracy of reading the value of this curve, and it is not so tough, it's not so strict. Did you grab my idea? In short, you can reach one like a 180 or 210, 210 ampere per meter. It is okay.
Okay.
Okay, once we found H, we can take a look at the last equation sheet. It says that line integral of H dot En alongside the average line length here is Ni. On hand, we knew that because H here is a constant, so the left side here is H, times the average length, which is L. And from here, you see, we can find very easily the current. Are you okay? So I will summarize the technique here. So in this exercise, we start from the magnetic flux phi, okay? And from the magnetic flux, we find the density. Using the first equation, phi is Bs. And from the density here, we can use the given curve to find the corresponding MF phi. And from H, we come to the final answer, which is the current. So this is a forward exercise. Given phi, we have to find I. If we are given I and we have to find phi, then it is a reverse problem. The reverse problem is normally harder than the forward problem. So any question for this? Is everything okay? All right, so if everything is okay, then please do this exercise. I will ask you to do the reverse exercise. Let's suppose that the current here is 0.2 ampere. Then I want you to find the magnetic flux. Okay. All right, go ahead. You got 6 minutes.
Excuse me.
Yes.
First I apply the formula the integration of h dot dl.
Okay.
Equal the so I find the magnitude of magnetic equals 500 over 3. So how do I find the magnitude of B?
You can take a look at this. What is the value of H? It is about 200
500 over
3. So
yes.
I guess this is about 160, right?
Yes.
This one is let's say that it is 160. So this one is 100. This one is 175. So 160, you get back a little to the left. This is 160 approximately, and then you go up. You come to this cross section, okay, and then you go to the left. Then B will be 0.8. Is that okay?
Yes. Yes.
Okay, it's break time. 10 minutes. Okay, let's get back to work. This is the second example. This one is little harder than the previous one. Because the code here you see is a little more complicated. It consists of 3 sessions, number 1, number 2, and number 3. They are different by the cross-sectional area and by the length, of course. Once again, the relationship between B and H are given. Is here, this curve. In this exercise, we are given the magnetic flux and we have to find the current. So this is once again the forward exercise. The three sessions here are in series, so they will have the same magnetic flux. The very same magnetic flux flows through the all 3 sessions. So we understand that phi 1, phi 2, and phi 3 are equal. So because the S1 and S3 are the same, so we can find B1 and B3 together like this. Are you okay? And like the previous exercise, from B1, from this value, we can find the corresponding H. Okay, according to this plot, this figure, this characteristic curve, we can find H1 and H3. Of course, they are the same. Okay, so that was story about number 1 and number 3. Now we turn our attention. We turn to number 2. B2 is phi over S2, and we got this. And once again, from B2 here, we can find H2. The question here is to find the current, so we can rely on Ampere's law to find the current. The right side here is the number of turns multiplied to the current. The left side here is the line integral alongside the average length of the core. And like I told you, because we suppose that H here are constant, so the left side here can be broken up down into 3 terms alongside the 3 sessions, number 1 and number 2 and number 3. From this, we can find the current, okay, because everything here was found or given. And finally, here are. So like I told you, this one is a forward exercise. We are given the magnetic flux, and we can find the current. But if we try to do the reverse problem, the solution is a little harder. Okay, why did I say that? Because let's imagine that we are given current. Let's say that current is 0.5. So if we are given I here, how can we find H1, H2, and H3? The answer is impossible. You know why? Because we have here only one equation. On the other hand, we have 3 unknowns, H1, H2, and H3. So we cannot find them. Can you get this idea? In this exercise, the forward problem is very simple, but the reverse problem is a little harder. How can we deal with this? We can apply a spacing method. Let's say that it is the estimation method. Okay, we come to the exercise number 3. Actually, this one is very similar to the previous one, except one thing. This is a reverse problem. You see, we are given the current and we have to find the magnetic flux. So on the previous page, I told you that we theoretically cannot find the magnetic flux from the given current because we have to rely on the a multi-variable equation. So the solution here is the estimation method. Okay. The idea here is that because we cannot solve for the reverse problem directly, so we will solve for the forward problem many times to estimate the solution for the reverse problem. Okay. Okay, I will try to explain this. In the estimation method, we suppose that the magnetic flux is 1 milliweber, like this. Okay, and we apply the forward method to find the corresponding current. And I will go through this one very quickly because we did this in the previous exercise. Okay, so with the assumption of 1 milliweber here, the answer here is 0.318 ampere. Is this okay? No, this one is not okay because according to the exercise here, the current must be 0.5, not 0.318. So our assumption here, our assumption here is incorrect. Are you okay with this page? So our first assumption is incorrect, but our advantage here is that we have time. So this is our first try, okay, our first estimation. We can try another one, okay, and we hope that by doing that several times, we can finally come to the exact answer. Okay, we return to this. According to this, if phi is 1 milliweber, then the current is 0.3, which is smaller than this. So I'll try another estimation. I will increase the magnetic flux here a little, and I hope that when I increase phi here, the current increases also. Okay, so I try another assumption. I suppose that the magnetic flux is 1.2, and applying the very same procedure, we finally come to this. Okay, do you know this method? We can say this one is the estimation method or try and error method. The bad news is that we still haven't found the current, the answer, because this one is a little greater than the given current. Okay, but the good news is that we circled the answer. You see, the answer is somewhere between 1 and 1.2 because the current here is how can I say, is before and after the given current. Are you okay? So until now, we have two solutions, two choices. The first one is that we try another value of phi. Okay, let's say it is 1.1, for example. The second choice is that normally the relationship between the current and the magnetic flux here is nonlinear. But approximately, I can suppose that the relationship between the current and the magnetic flux here is linear. And I can approximate that by the first order polynomial like this. This is just the assumption, okay, an approximation. And if you want to find this new relationship, we have to find out A and B. And we can do that relying on our two tries here. Okay, when phi is 1 milliweber, the current is 0.318. When phi is 1.2, the current is 0.538. Okay, so from here I think that I think everybody can find the two coefficients. And here we are. The relationship here was found. Okay. And according to the requirement of this exercise, the current must be 0.5. So you can change I here into 0.5. And finally, we have the approximate result of this exercise. Are you okay?
Why would you know the the magnetic flux and current has formed first order polynomial, and they are linear.
Yeah, actually the relationship between I and phi is nonlinear, and I don't know that relationship. I don't know the relationship, but approximately I suppose that the relationship between I and phi is a straight line. Okay, that is just approximation. If you don't like this, you can try some further tries for this one. Okay, you can say that I suppose that phi is 1.1, then I find the corresponding I, and you can repeat that try several times. And finally, I hope that you come to this one. But this method is easier. This one is, do you know this is the name for this one? It is the interpolation. Okay, we can interpolate the value in the middle of two already known values. If you want to have how can I say a more accurate relationship, you can suppose this one is a second order polynomial, a parable. Okay, but in that case, you have to have three choices instead of two like this. Okay, finally, this one is just my assumption.
Okay, I see.
All right.
Try later.
Okay. So, do you guys have any other question about this method? Is everything okay?
Excuse me, teacher.
Yeah, go ahead.
So why can't we do the reverse method like previous?
Can you say it once again, please?
Why can't we do the reverse method like previous exercise?
Yeah,
Like we know.
because in this exercise, this is a relationship. Look at this. This one is the equation. And in this exercise, because when we are given the current I here, okay, and you can see that on the left side, we have three unknowns, H1, H2, and H3. So we knew only I here. Of course, we knew N here, but we are given the left side, the right side here. So from the right side here, we cannot find H1, H2, and H3 because we have only one equation, but there are three unknowns. Are you okay?
Thank you. Yes, thank you.
Never mind. Any other question, guys? Is everything transparent? Okay, so I guess I can keep going. Exercise number 4. In this exercise, the core here is very simple. It has only one cross-sectional area, but we have an air gap. The air gap here is very narrow. It is only 2 millimeters. Okay. Then once again, we have to do the forward problem. We are given the magnetic flux and we have to find the current. Firstly, we can find the magnetic flux density of the core. It is 5 rs. And once again, from the just found B here, we can rely on the curve here to find the corresponding H. Approximately, it is 60. Okay. Now when B is the air gap, for the air gap here, do you remember the previous exercise? We knew that in the air, the magnetic flux is perpendicular to the surface of the magnetic material. So this is a magnetic flux in the air. You can see that it extends a little to the left and to the right. So the cross-sectional area of the air gap is a little greater than that of the core. So from now on, to find the area of the magnetic of the air gap, you have to increase two edges of the core here by 1/10%, like this. Sorry, by 10%. Okay. And from this, we can find H. Sorry, give me 2 minutes. Sorry about this.
Teacher, I have a question.
Sorry guys, I have a family issue. Sorry once again. Okay, so do you have any problem, any question for this? Is this okay? For the A, please notice that the relationship between H and B is very simple. B is the mu0 H, so we don't have to use the curve here to find H from B and vice versa. Please notice that H of the core is much smaller than that of the air. Okay, because the permeability of the air is very small, so in order to maintain the same magnetic flux, MFI in the air must be very high like this. Okay, so now we come to the answer. We found H of the core and that of the air gap, so we can use Ampere's law to find the current. Okay, if we apply Ampere's law alongside the average length of this one, we can have this, and from here you can find the current. Is this okay? Okay, the last exercise, the last example. This is very complicated. I'm talking about the configuration of the core. And to find this, we have to rely on these equations. And try to explain this. So, why do we have these equations? You can think of a corresponding magnetic flux. So, sorry, give me 1 minute. The core here, you can think of the core here like a voltage source. Remember this in linear circuits? Okay, and the first core, the section number 1, is a magnetic resistor. It is connected in series with the source, the voltage source, and the two other sections, number 2 and number 3, they correspond to two other magnetic resistors like this. And here we have the, let's say this one is the corresponding circuit. The voltage source here is Ni. This is the resistor number 1, number 2, and number 3. Number 2 and number 3, they are in parallel. Okay, you see that? All right, so the voltage source here, I'm talking about Ni, it produces a magnetic flux, phi 1. At this point, phi 1 is divided into two other currents, we can say that. They are phi 2 here and phi 3 here. Okay, this current is phi 3. So you can see that applying KCL, remember that, to this node, we have this equation. Okay. For this one here, you can see that when we go from this point to this point, there is a scalar potential, how can I say, there is a scalar magnetic potential. The scalar magnetic potential from here to here is S3 times N3. And we know that this point is also the starting point and the ending point of the of the resistor number 2. So for the resistor number 2, the scalar magnetic field from here to here is also S2 and 2. And because the two resistors here are in parallel, so they must have the same potential. So we got this. Finally, for this equation here, you can see that applying the KVL to this loop, you can see that the voltage across one is N1, is H1 N1, plus the voltage across one is N2 H2 must be equal to the voltage source, which is Ni. Okay, in short, applying KVL to this node, we have this equation: F minus H1 N1 is equal to H2 N2. Are you okay? So, in short, applying KCL to this node, I have the first, this equation. Applying KVL to this loop, I have this equation. And applying KVL to this loop, I have the last equation here. Are you all right? Okay, so we have here three equations. How can we use them? Firstly, I will give an example. Let's do firstly the forward problem. Okay, let's suppose that we are given F53 and we have to find the current I. How can we do this? So we apply this one from F3. From phi 3. What can we find, guys? What can we find from phi 3, guys? It is a B3. Okay, B3 will be phi 3 over S3. And then what's next? From B3, you can use the curve, the given curve, to take a look to find the corresponding value of S3. Are you okay? And then what? Knowing S3, how can we find? What can we find, guys?
Current.
Yes, sorry.
Current. I3.
The what? Sorry.
I3.
No. From S3 here, we can find S2.
H2. Okay.
Okay, according to this one. Because we are given N2 and N3, so we can find H2. Okay. Anyway, thanks. All right. So from H2, how can we find? What can we find? What's now? Please notice that we have only three quantities: phi, B, and H. That's all. Okay. So from H2 here, we can find B2. And how? How can we find B2? We use a given curve. Okay. From the given curve, we can constant to find the corresponding B2 if we know H2. And then what's next, guys? What now? B2? Okay, if we are given B2, we can find phi 2. Phi 2 will be B2S2. Okay. And what's next? From phi 2, what can we do? What can we do now?
Phi 1.
Yeah, that's right. We can find the phi 1 from this equation, okay? Because we are given phi 2 and we just found phi 2. We are given phi 3 and we found phi 2. So yeah, we can find the phi 1. And then what now? From here, we can find B1. B1 will be phi 1 over S1. Can you help me to fill in here? What now?
H1.
That's right. We can find H1. How can we find H1? We use a curve. Okay, we use a given curve. And okay, you see, we found H1, we found H2, we are given N2 and N1. From here, we now can come to the final answer, I. Đây quá. So because you see that, because the circuit here is very complicated, so the process of finding the current here is very long, much longer than the previous examples. Are you okay? This is the most complicated magnetic circuit. If you can go through this exercise, you can do any other exercises. I mean, any other exercise about magnetic circuit analysis. So, any question for this? All right, and to finish this very important session of this chapter, I ask you to do the last mid-class exercise. This is not very complicated. It is a forward exercise. You are given phi 1, and you have to find the I, the current. So I want you to write down the process of finding finding the current from phi 1. Okay. Okay, off you go, guys. 10 minutes.
Excuse me.
Yes.
Uh, at the favorite exercise,
Yes.
which is exercise number 5. How do we find um, um, B B3 from magnetic flux?
B3
Theta
is
3.
phi 3 over S 3.
Yes. How we find
Yeah.
B3?
From phi 3.
Yes.
This is the equation. Phi is a BS. Okay. So B3 will be phi 3 over S3.
Over.
Yeah.
Okay, but in this exercise we don't have the mark the the area.
Oh, we are suppose that we are given the physical perimeter of this exercise, this circuit. Okay. So we knew N3, N1, N3, N2, and we knew B1, B2, B3. Sorry, S1, S2, S3.
Okay. What is F? What is the quality of F? Quality F.
Sorry.
What is F quality?
What can you say it once again? I can't get you.
What is F?
F.
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 Yes.
Quality.
In
F
the
is Ni. F is Ni.
yes, in the figure, in this figure.
Here in this figure, F is Ni.
The total current.
Okay, give me 1
All right.
minute. F here is the number of turns multiplied to the current. F is Ni.
Okay.
F is the electromagnetic force, EMF.
Okay. I see. Total magnetic force to the area.
Okay, any question? Okay, so that's all for today. See you next time. Goodbye.
Goodbye, teacher.
Goodbye.